Hi everyone, welcome to Chapter 21. This is our last lecture in Chem 2. Today we are going to cover a little bit of organic chemistry, and this should mostly be review from Chem 1. In Chem 1, you likely learned how to name alkanes, which are singly bonded hydrocarbons. Today we're also going to learn how to name alkenes and alkynes, so hydrocarbons that have triple bonds and double bonds. So that's where we're going today, and like I said, this is the last lecture in Chem 2. So here we go. So, brief introduction to organic chemistry, just because I know some of you may be moving into OChem next semester. So organic chemistry is a branch of chemistry that focuses on compounds that contain carbon. Okay, they may contain other things, but it's mostly carbon and hydrogen, maybe a little bit of nitrogen, oxygen, sulfur here and there. And so this doesn't include things like carbon monoxide and carbon dioxide, carbonates and carbides. These are going to be chains of carbon atoms that are bonded together. And so even though these organic compounds only contain a few elements, the ways that the carbon atoms are attached to each other and the ways that they form molecules will lead to millions of different organic compounds, which is why the field of organic chemistry is so big, right? It's a huge field of chemistry, and I think it's super interesting. Today, like I said, we're just going to learn some nomenclature, but organic chemistry as a whole is really interesting, and so I highly encourage you to take organic if you have the opportunity. So, why is carbon unique? Carbon atoms do things that other atoms don't, and the main thing is that they can form 4 covalent bonds. And so can some other atoms, right, like sulfur, but carbon forms really non-polar bonds, especially with hydrogen, right? So we can have these long chains of carbon atoms that can bond to each other, and they can also bond to hydrogen. And these bonds, because the electrons are being shared equally between the 2 carbon atoms, or being, mostly equally between the carbon and the hydrogen atoms, they are really non-polar. They're very strong and pretty non-reactive, okay? They're really strong because both of these atoms, right, carbon and hydrogen, have similar electronegativities, and they're both pretty small atoms. So we tend to form really strong bonds. So carbon atoms concatenate, which means that they can form chains, right? So we can work with, 2 carbon atoms that have been bonded together like in ethane, or you can get 10, 20, you can get, 30 carbon atoms all bonded together, or even more, right? These carbon atoms can form single bonds, or they can form double bonds, or they can form triple bonds. So here you've got a double bond in ethene and a triple bond in ethyne. And so the endings of these, A and E is going to tell you it's all single bonded. E and E is going to tell you there's a double bond, and Y and E is going to tell you that there's a triple bond, which we're going to go over in this lecture. These carbon atoms can form these long chains, or they can form rings, which also gives them some really cool properties. So hydrocarbons contain only carbon and hydrogen. You'll get into other molecules that have oxygens, like carboxylic acids or ketones or aldehydes or alcohols, right? You can have nitrogens that form amines and amides. You can have sulfurs, but mostly they're going to contain carbon and hydrogen, and that's what we're going to work with predominantly today. They are insoluble in water because all of these bonds are non-polar. So when carbon and hydrogen bond, right, they form a non-polar bond. And when carbon and carbon bond, obviously they form a non-polar bond. And so all of the bonds in this molecule, or most of them, tend to be non-polar, which makes them really insoluble in water. So we have 2 different types of hydrocarbons that can exist. You can have aliphatic hydrocarbons, and what that means is they can be mostly single bonds, or they can have maybe 1 double bond or 1 triple bond, but they're very few, okay? And so when we have saturated aliphatic hydrocarbons, that means that we're going to have alkanes. They are saturated with hydrogens. It's the maximum amount of hydrogens that they can have, right? There's no double bonds, there's no triple bonds. All of the electrons are going into forming bonds with either carbon or with hydrogen. When we have unsaturated, that means that there are alkenes or alkynes because some of those electrons got tied up in double bonds or triple bonds. So these aliphatic hydrocarbons can either be in chains or rings, but they're going to be mostly single bonded with maybe a double bond or a triple bond here and there, but not very many of them. The chains can be either straight chains or branched chains, and we're going to look at those a little bit later. Aromatic hydrocarbons are going to be hydrocarbons with benzene. And they're going to have alternating single and double bonds. So it'll go, double bond, single bond, double bond, single bond, and they'll go in a pattern, which gives them really cool properties. Okay, we're not going to look at aromatic hydrocarbons in this class, but they are a large focus of organic chemistry as a whole. So we are going to look today at aliphatic hydrocarbons. We're going to look at alkanes, alkenes, and alkynes. We're going to save aromatic hydrocarbons for a different class, although it is covered in this chapter, in chapter 21 in your textbook. We are not doing all of chapter 21. We are just doing a brief portion of it to get you ready for organic chemistry. So here's some of the uses of hydrocarbons. If we have very few hydrocarbons like methane, ethane, propane, right? Those are used as gasoline, right? Or not as gasoline, sorry, as a gas to burn things like, maybe you're barbecuing in the backyard, right? You might have some propane. And then if we have more carbons, right, then we'll get low boiling liquids that we use as solvents in class, like hexane, right? We've worked with hexane that has 6 carbons, or gasoline, right? And as we get more and more and more carbons, you can see that we're changing the state. We're going from a gas, and eventually if you get enough carbons, then you can make a solid like petroleum jelly or paraffin wax, right? And that's because we are getting more and more dispersion forces, right? The larger our long hydrocarbon chains are, the more electrons that are in them and the more polarizable our molecule has become, and we'll have an increase in those intermolecular forces, and, we can have solids, right? But again, all of these different lengths of chains have different uses, and they will do different chemistry. So here we go, just to kind of start us off. We're going to start with alkanes. We're going to have all single bonds in our alkanes. And the way that we find the formula of the hydrocarbon will be, we'll have some number of carbons, maybe it's 6. And then the way that we find the number of hydrogens that goes with that number of carbons, it's always going to be 2 times the number of carbons plus an additional 2 for the, these hydrogens that are on the ends here. Okay, and then alkenes are going to be carbons, and then the way that you find your hydrogen will be 2 times the number of carbons. And alkenes will have 1 or more double bonds. And then alkynes will have 1 or more triple bonds. And the way we do that is we'll do, our number of carbons and then 2 times our number of carbons minus 2 to find out our hydrogens. And these formulas are taking into account the fact that some of the, the possible hydrogens that could exist if this was saturated have now been tied up. Those electrons have been tied up in a double bond or a triple bond, so we have fewer hydrogens that can bond to those carbons. So first, let's talk about the types of formulas. We have worked with molecular formulas. Those show the kinds of atoms that are in the molecule, but they don't necessarily show how they are attached. Sometimes we'll write them in a certain order to kind of indicate how they're attached, but if I just told you, C6H14, right? That's hexane. That doesn't tell you anything about how those carbons are arranged. Okay, so that would be a molecular formula. A structural formula shows you the attachment pattern in the molecule. That's these down here. These are structural formulas. And then sometimes we'll look at models. We have a couple slides that have models on them. They'll show you the attachment pattern, and they also give you an idea about the shape of the molecule. If you'll remember, in Chem 1, you did a molecular models lab that had you start looking at shapes of models with those, right? So instead of just looking at these 2-dimensional structural formulas, you can use those model kits or even models on the computer to see the shape of the molecule. So again, a structural formula just shows how those atoms are arranged in the molecule and how they are bonded. Okay, sometimes, writing out these structural formulas like you see, right, these only have 4 carbons in them, right? We have butane and we have isobutane, which is a branched butane. But either way, even though there's only 4 carbons here, they're starting to take up a lot of space. And so we'll write them as the condensed structural formula sometimes, just to save room. So this one, this butane here, instead of showing all of the carbons bonded like that, you can write that like this. Okay, so that would be a condensed structural formula. Okay, and you can show the dashes here if you want, but sometimes we'll leave them out. And then other times you'll see the carbon skeleton formula. Sometimes we'll call that a line formula, and it shows the carbon-carbon bonds only as lines. So instead of writing all of those 4 carbon and hydrogen groups out, we would write it like this. Okay, that would be the carbon skeleton formula or a line formula. Just so you know, if you get into higher levels of organic chemistry, this is what people will use because it's just showing the carbons. And if it's not a carbon, we're going to assume that it's going to be a hydrogen. So we don't need to go around writing all of these hydrogens all the time because there are lots of hydrogens to go around. So just show how the carbons are connected. And so structural formulas, either any of these, right, whether we're looking at the structural formula on the previous slide or the condensed structural formula or the carbon skeleton formula or the line formula, all of those are two-dimensional. And so sometimes they don't give us a really accurate picture of what the molecule will really look like. In higher levels of organic, you'll learn ways to draw them in 2 dimensions on your paper, but make them look like 3 dimensions, which is really cool. You'll have, wedges and dashes and all kinds of things. But for now, we'll say that these are 2-dimensional and our space-filling or ball and stick models are 3-dimensional. But we're just going to work with 2-dimensional for now. All right, let's talk about structural shorthand. So this line formula, right? So this is butane. And like I said, I've left off all the hydrogens here that you would normally draw just to make it, cleaner and easier to see. Otherwise, you start to lose all of these carbons. So here's a carbon, here's a carbon, here's a carbon, and here's a carbon. So we could go through and write C's, but an easier way to remember it is that every end and every bend is a carbon. So each end is a carbon, and all of the bends are carbons as well. And then if it's not a carbon, then it's a hydrogen. And if it's not a hydrogen, then we would show an oxygen or a nitrogen or something like that. But if it's an end or a bend, it's a carbon. And if it's not shown, then it's a hydrogen. So there's the first carbon, the second carbon, the third carbon, and the fourth carbon. So again, we don't have to go through and write all of these carbons and write all of these hydrogens all the time. We just draw these line structures. All right, let's talk about alkanes. So these are saturated hydrocarbons. So alkanes will have all carbon-carbon single bonds. And like I said, it's saturated with hydrogens. It has the maximum amount of hydrogens that it can. Okay, our formula will be, some number of carbons. And then the way that we find our number of hydrogens is we multiply the number of carbons by 2 and then add 2, again, like I said, to represent those carbons on the end. If we have a ring alkane that has all carbon-carbon single bonds, we won't add the +2 at the end to figure out the number of carbons because the carbons on the ends have been connected to each other instead of connected to hydrogens. But that's how you'd figure that out. So we have some prefixes that will tell us how many carbons are in our chain or are in our ring, right? And so these are our prefixes here. You do need to have these memorized. Hopefully you worked on this in Chem 1, and this is just a refresher course, but meth means 1, eth means 2, prop means 3, but means 4, right? And so these prefixes you need to know. Some of them are similar to the prefixes that we used when we learned covalent bonding, right? Like, pent means 5 in both of those, hex means 6 in both, but the first 4 are different. Okay, so if we use these prefixes and we're just talking about a straight chain, then that will tell you the number of carbons in the chain. So let's take hexane, right? Hex means 6. So that's telling us that there are 6 carbons in our chain. And the way that we would figure out the number of hydrogens, remember hydrogens are going to be 2n plus 2. So in hexane, we would say 2 times 6 plus 2. So 12 plus 2 gives us 14. So that's why hexane is C6H14. Okay, so the prefix will tell you the number of carbons, and then you can use this 2n plus 2 to figure out the number of hydrogens that go with that number of carbons. So this gives us the molecular formula here, and then you could write out the condensed structural formula, by writing, the CH3s always go on the end, and then CH2s will go in the middle of the chain. So let's try this. I want you to go ahead and pause here and try this out. So you're going to name the first 2. Again, you're going to need to know those prefixes. So if you've forgotten them, write these down and go back to the previous slide so you can see the prefixes. but you'll name the first two and then write the formula for the last three. And I just want the molecular formula. You don't have to do the condensed structural formula at this time. So go ahead, pause here, and then come back when you're ready to see the answers. All right, let's go over this. So this first one is C5, okay? So we know that this is going to be pent something, right? And then we would check to see if it's alkanes, alkenes, or alkynes. Right now it says it is an alkane, so we don't need to check that. The way that we would, though, is you would take this number of carbons, and then you would multiply it by 2, and if it's equal to multiplied by 2, then it would be an alkene. If you have to add 2 hydrogens, it's an alkane. If you subtract 2 hydrogens, it's an alkyne. But again, these are all alkanes, so this is pentane for now. So again, alkanes are always going to end in ane, which tells us it's singly bonded. And then we have C7H16. This is hept because of that C7. And again, we don't have to go through and check. We know this is heptane because it says it's an alkane. And then to write the formula, dec means 10, so we go C10. And then to figure out our number of hydrogens, we go 2 times 10, which will give us 20, plus 2, so that's H22. And then prop means 3, so we go C3, sorry. And then hydrogen, we go 2 times 3 plus 2 gives us 8. And then hexane, we've done before, C6H14. Okay, so that's how you do those. That's alkanes. So now we're going to go ahead and name them when they're not just these long straight chains. A lot of times we don't have long straight chains. We will have something coming off of our chain. Okay, so this is going to teach you how to name it when there's not a straight chain. There's something coming off of it, a branched chain. Okay, so we will first figure out the longest continuous carbon chain. And then you'll count up the number of carbons in that continuous carbon chain, and that will give you the base name of the compound. So if there were 8 carbons, it would be octane. So again, though, you're just looking at the longest chain. And again, the prefix for alkanes, or sorry, the base name, you're going to have the prefix, and then you're going to end it in ane for alkanes. So then we will go through and look at what is attached to our base chain. So anything that's attached to the base chain, we are going to call a substituent. So this can be carbon groups, it can be halogens, it can be, later you'll learn about, if there's an oxygen bonded to it and how is the oxygen bonded to it. But for today, we're going to look at carbon groups, carbon with some hydrogens, or we're going to look at halogens. Those are our 2 options for today. So these will be substituents, things that are attached to the base chain. So the prefixes for these substituents are going to be the same as the prefixes that we're using for the base chains. So the good thing is you don't have to memorize more prefixes. So as long as you know them for the base chains, you also know them for the substituents. So this is going to talk through how to name these. Okay, so we're going to go through it step by step, but this is just a good summary slide if you're looking for something to reference. So the first step will be to identify the longest carbon chain, and again, that will be the base chain. Then you're going to name any branches as alkyl groups. And this just means any carbon base or carbon chains that are attached to your base chain. If you have more than one substituent that contains carbon or more than one substituent in general, you're going to name them alphabetically. Okay, you're going to number the chain from the end that's closest to a branch of some kind, closest to a substituent. And if they're, equal distance, then you'll, figure out which one will give the next substituent the lowest number. This will make more sense as we go through it, but you want to end up with your substituents having low numbers. And then you're going to write the name of the compound, and you're going to use dashes and commas, and we'll show you as we go through that. And then if you have more than one of a substituent present that's the same, you're going to use di, tri, or tetra to tell you how many of that type of substituent you have. But this prefix doesn't count in your alphabetizing. So let's go through this. This will make more sense as we practice. So again, the first thing you're going to do is figure out the longest continuous chain of carbon atoms. Okay, so there's 2 different ways we can go for this one. We could go this way, or we can go this way, right? Either way, we're going to end up with 4 carbons in our longest chain. So I've chosen to go along the top here, right? And there are 4 carbons in that chain. So our root name for this chain is butane because there are 4 carbons and they are all single bonded. Okay, so now if we have an alkyl group that appears as an substituent, again, you're going to name them using those prefixes, but instead of saying methane, propane, butane, right, we're going to now end in YL. So it'll be methyl, ethyl, propyl, butyl. So again, these are when these groups are attached to your base chain. We'll name them as a substituent. So here, that group, that carbon-hydrogen group, there is only 1 carbon in it that's attached, right? We don't include the carbon that's in the base chain. So there's just 1 carbon in this substituent group, so we call this a methyl group, since it's a carbon-hydrogen group that's attached to the base chain. If you had, a halogen, so maybe you have chlorine or fluorine or something like that, right? You'll name it as the halogen's name, but you'll take off, the chlorine and you'll name it chloro, or fluorine becomes fluoro. Okay, and that's how we'll name the halogens. Again, those are the only types of substituents we are going to deal with in this lecture are either carbon-hydrogen groups or halogen groups. So now that we've figured out what the name of our substituent is, we have to give it a number to tell us where it is on the chain. So this is a methyl group, and again, remember our numbering. Okay, so the reason that we're numbering it this way, right, 1, 2, 3, 4 from left to right, instead of going 1, 2, 3, 4, is because when we number it from left to right, our substituent is on the 2nd carbon. Okay, if we had numbered it the other way, from right to left, our substituent would be on the 3rd carbon. And we always want to give our substituents the lowest number possible. So that's why we're numbering it the other way. Okay, so now that we know it's on the 2nd carbon, it's called a methyl group, we know our base chain is butane, we can put it all together and we can name this 2-methylbutane. Okay, so anytime you have a number and a word, you're going to use a dash to separate the number and the word. If you have 2 numbers, and I know that we don't right now, but let's say there was, another methyl group on the 2nd carbon, you would name this 2,2-dimethyl-butane. Okay, if there were 2 carbons, if it looked like this, if we go 1, 2, 3, 4, and if there were 2 groups on that 2nd carbon. Okay, so anytime we have 2 numbers, we're going to separate them by a comma, and if we have a number and a word, we're going to separate it with a dash. So let's go ahead and try this one. This is much more complicated, right? We've got a lot more going on. It's a longer chain. The first thing, though, that you're always going to do is figure out the longest carbon chain, the longest continuous carbon chain, and that will give us the base name. So go ahead, count your carbons, figure out the base name for this hydrocarbon. All right, so if we go along and we find our longest carbon chain, again, I've numbered this from left to right now, just counting carbons, but there are 9 carbons in this longest chain, so we call this nonane. So then we have to figure out, okay, what's on our carbon chain? Okay, so anything that's not, not in this long carbon chain here, they are going to be substituents. Okay, so we have 2 different methyl groups, right? Because we have 2 different groups with just 1 carbon. And then we also have a chlorine, so this will be a chloro group. So now we'll give them numbers. So as you can see, I've numbered it right now from left to right, and that will give our substituents a 2, a 3, and a 6. But if we had numbered it the other way, right? Right? If we had numbered it the other way, then our substituents would have a 4, a 7, and an 8. So those would be higher numbers, and we always want to give our substituents the lowest number possible, which is why we're going to number this from left to right. So we have a chlorine group on the 2nd carbon, and we have methyl groups on the 3rd and the 6th carbon. So when we name our substituents, we're always going to go in alphabetical order. So chloro comes before methyl when we're naming this because, C comes before M. And I also want to point out before I start naming this that there are two different methyl groups. Therefore, we are going to name this dimethyl when we get to it. Okay. So again, you want to figure out the numbers, and we're going to number this 1 to 9, not 9 to 1, because we want to have the lowest numbers possible. All right. So now we are going to name this, again, the chlorine's going to come first. So this is 2-chloro. And then we have our methyl groups, 3,6-dimethyl-nonane. So like I said before, anytime you have a number and a word, you're going to use a dash. Okay, number, word, dash. And anytime you have two numbers, you're going to use a comma. Oh, here's another number, word. Okay, so number to word, dash, number to number, comma. Your substituents go in alphabetical order. So we have chloro and methyl. The di here, even though, chloro comes before di, the di doesn't affect our alphabetizing because it's a prefix, right? It's a prefix essentially on our prefix. But we don't include the di. That's just telling us how many methyl groups there are. And then the numbers are telling you where your substituents are at. The chloro group is on the second carbon. The methyl groups, and there's two of them, right? The methyl groups are on the third and the sixth carbon. And then the longest chain has 9 carbons, and they are all single bonded. So lots of information in these names for these organic compounds. So I want you to take what you've learned and go ahead, pause here, and try to name these branched hydrocarbons. And then once you're done, come back and we'll go over the answers. All right, let's go over this. So this first one, we have, again, we always figure out our longest chain first, right? We have 1, 2, 3, 4, 5, 6, 7. So this is going to be heptane. And we're going to give our substituents the lowest number. So it looks like we're going to number it from left to right instead of right to left because they seem to be closer to the left side. So we go 1, 2, 3, 4, 5, 6, 7. Okay, so our two groups are on the third carbon. So they are going to be 3, 3. And these are both methyl groups because they don't have any bends in them. They just have an end. So that's 1 carbon and that's 1 carbon. Again, we're not going to count this carbon. That's in our base chain. So these are both methyl groups. So this will be 3,3-dimethyl heptane. All right, let's try the next one. So again, we are going to, figure out our base chain. So you could have chosen either path. You could start up here or you could start down here. Either way, there's 2 carbons in each of these, so either one is going to be fine. I'm going to start numbering it from right to left instead of left to right because it looks like this substituent is closer to the right-hand side. So go 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9 carbons in our base chain, so this is going to be a nonane, and our substituent is on the third carbon here. And you'll see that there is 1 bend and 1 end, which means that there are 2 carbons in that substituent. So that is an ethyl group. So this is 3-ethyl nonane, right? We have an ethyl group on the third carbon, and there are 9 carbons in the base chain. All right, last one. We'll go ahead, we'll count the carbons in our longest chain. I'm going to number it from left to right because it looks like our substituents are closer to the left-hand side. So you go 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is going to be nonane again. And we have 2 substituents. We have 1 here and 1 here. Okay, so we have 2 different ends. So they're going to be 3,6-dimethyl-nonane. All right, let's move forward. So now we're going on to aliphatic unsaturated hydrocarbons. So aliphatic means, again, that they may have 1 double bond or 1 triple bond. Maybe they even have 2 double bonds, but they're not going to be in this alternating pattern of double, single bonds. Okay, so alkenes is what we're going to talk about first. Those are going to include double bonds, and our formula is going to be our number of carbons, and then our hydrogen will have 2 times that number of carbons. Okay, they're going to have 2 fewer hydrogens than the alkanes because those electrons that would normally go to a hydrogen have now been tied up in a double bond. They're going to have trigonal planar geometry around the carbon because if we think about like ethene, looks like this. There are 3 areas of electron density around each of the carbon, right? The double bond and then 2 bonds going to each of those hydrogens. So they're trigonal planar, which means that they're flat. Instead of in our alkanes, they have tetrahedral geometry around all of those carbons because they have 4 groups. Okay. So ethene, you may actually have heard of ethene before, or maybe ethylene. Okay, these are actually the same thing, they're just different ways of naming it. Ethene is the IUPAC name that we are going to use, but it's produced by ripening fruit, and we use it to make polyethylene. It's really easy to use in polymers because of that double bond. But there you go. This is the space filling model that I was talking about earlier that shows you how these atoms are arranged in space, and it more shows how they are taking up space in the molecule, essentially. All right, so here's some different alkenes. So we have ethene. Again, eth means 2 carbons, prop means 3 carbons. 1 butene, that's going to tell you that there is a double bond attached to the first carbon, and the butene obviously means that there's 4 carbons with 1 double bond. So the way that we're going to start naming these is that there is going to be a number in the front now of our base chain that's going to tell you the location of the double bond. And it's only going to tell you the first carbon in the chain that the double bond starts. Obviously, it would also go to the next carbon as well. Okay, so these are all 1 because the double bond starts on the first carbon in the chain. And we're always going to number our chain to give our double bond the lowest number. So alkynes are also aliphatic unsaturated hydrocarbons. Again, they're not having a repeating pattern of double, single, double, single. That's why they're aliphatic and not aromatic. They contain a triple bond. And their formula is going to be our number of carbons and then 2 times our number of carbons minus 2 to represent the electrons that are tied up in that double bond. So if you had your alkane formula, you would subtract 4 electrons, 2 for each of the bonds. And they have a linear geometry. So here, we'll draw this guy, ethyne. Okay, and again, they have 2 areas of electron density, which makes this linear. So here are some alkynes. Again, the number in front of our base chain is going to tell us the location of the triple bond. And we're always going to number our chain so that our triple bond has the lowest number. The rules that apply to alkenes are going to be the same as the rules that apply to alkynes, just there's going to be a triple bond instead of a double bond for alkynes. So acetylene you may have heard of. So ethyne is also called acetylene, and it's used in welding torches. So there you go. All right, let's go ahead and learn how to name them. Alkenes and alkynes are named exactly the same way as alkanes. The only differences are that our base chain has to contain the double bond or the triple bond. So even if you have a longer chain of carbons that's happening, you have to go and include the chain that has the double bond or the triple bond for naming purposes. Okay, so now instead of ending in ane for alkane, you're going to name it as ene or yne, depending on if you have a double bond or a triple bond. Like I said, you're always going to number the chain from the end closest to the multiple bond. So closest to the double bond, closest to the triple bond, and the number in front of that base chain will tell you where the double bond or the triple bond starts. So here's some examples. So our base chain here is going to be this, right? And so we can go through and count our carbons. We go 1, 2, 3, 4, 5, 6. So that's hex, right? And then there's a double bond in there, so that's hexene for our base chain. And then we have 2 different substituents, right? Both of them are methyl groups. So one methyl group is on the 3rd carbon, one methyl group's on the 4th carbon. So we call this 3,4 dimethyl, and then you'll see a new number here, right? We didn't have this number before. That number tells you the location of the double bond. So when we're numbering this, right, 1, 2, 3 is where the double bond starts. So we call this 3-hexene. All right, let's try the other one. This is our base chain running right through the middle here. And so we're going to count our carbons and we're going to number it from the side that gives the triple bond the lowest number. So even though if we numbered it from right to left, right, if we were numbering it going this way, then our methyl groups would have low numbers. But we have to go this way from left to right because we have to give our triple bond the lowest possible number. Okay, so we're going to number it this way: 1, 2, 3, 4, 5. Okay, and so there are 5 carbons, so that's pent, and then we have a triple bond, so that's pentyne. And then we'll look at our substituents. We have 2 different methyl groups again. They're both on the 4th carbon, so we say 4,4 dimethyl, and then again we'll say the location of the triple bond. It starts on the 2nd carbon, so that's 2-pentyne. All right, go ahead and try this one. This is our last problem for today. Pause here, try it out, and then come back when you're ready to see the answer. All right, let's go over this. So again, first step, going to count the carbons in our base chain, and we're going to start with the side that gives our double bond the lowest possible number. So we're going to start from the right and go left. So we'll go 1, 2, 3, 4, 5, 6, 7. Okay, so this is hept, and then there's a double bond, so this is heptene. Okay, we have a bunch of substituents. We have 2 different methyl groups, and we have an ethyl group. So remember, we need to go in alphabetical order. So when we're thinking about this, the ethyl group is going to come before the methyl group in our naming. Okay, so we'll say the location of our ethyl group, so that'll be 3-ethyl, and then we have 2 methyl groups, so we say 4,6-dimethyl. Then we'll say the location of our double bond, which is 1, and then heptene, right? So we have 3-ethyl, 4,6-dimethyl, 1-heptene. All right, and that is the end of today's lecture, and you have finished all of the lectures for Chem 2. You're done. Woo! Right? You've got a little bit of practice to do on naming these organic compounds, but like I said, hopefully this is mostly review from Chem 1, and this was just a refresher to keep your mind fresh. Otherwise, you've finished. Now all you have to do is to review for the final. You have the final review worksheet that's been posted in Canvas, so make sure you take advantage of that. It's just a selection, though, of practice problems. It is not all-inclusive. In order to really, really prepare for the final, you'll need to review all of those study guides that you've collected throughout the semester and do as many of the lecture worksheet problems from those actual chapters as you possibly can. You've got just about a week to prove how much you know about Chem 2. So make sure you really, really study and give that final your all. It's worth 20% of your grade, so don't take it lightly. You've got a lot of studying to do, but first, work on your organic chemistry and then study for the final. As always, if you have any questions on any of this organic stuff or anything throughout the course, please send your questions my way. I am happy to help you out. Otherwise, this is it. So I won't talk to you guys next time. It has been an absolute pleasure having you all in class, and I hope you've enjoyed Chem 2. Bye, guys.